We'll start with geometric sequences. A geometric sequence is a sequence in which each term after the first term is obtained from the previous term by multiplying it by a fixed non-zero real number. The fixed non-zero real number is called the common ratio for the geometric sequence and denoted using the letter R. As a quick example, the sequence 1, 2, 4, 6, 8, 16, etc. is an infinite geometric sequence with common ratio equals 2. It is a doubling sequence in that each term is double the previous term. Note that A2 can be obtained by multiplying 2 by A1, or equivalently, A1 can be obtained by multiplying A2 by a half. A3 is 2 times A2, which means A2 is 1/2 A3. A4 is 2 times A3, which means A3 is 1/2 of A4, etc. And this pattern, of course, continues indefinitely for an infinite sequence. Our development of geometric sequences will run parallel to the development of arithmetic sequences. In an arithmetic sequence, we can find the common difference, D, by taking any pair of consecutive terms of the sequence and subtracting the first term of the pair from the second term of the pair, as illustrated below for general terms an and an plus 1. This is, of course, the nth term, and this is the n plus first term. And the common difference D can then be found by doing this subtraction, an plus 1 minus an. In a geometric sequence, we can obtain the common ratio R by taking any pair of consecutive terms of the sequence and dividing the second term of the pair by the first term of the pair, as illustrated below for the general terms an and an plus 1. So here R will be an plus 1 over an. This, of course, will be the first member of our toolbox, which we'll be using to handle problems related to geometric sequences. As we did with arithmetic sequences, we're going to be interested in finding the nth term, which is also called the general term of a geometric sequence. Let A1 be the first term of a geometric sequence, and let R be the common ratio. Then A1 is, of course, just equal to A1, but A2 is going to be A1 times R. A3 is going to be A2 times R. Remember the previous term times R, but remember A2 itself is A1 times R, so I can write this as A1 times R, replacing A2 with A1 times R, which gives us A1 R squared. A4 will, of course, be A3 times R, but we know that A3 is A1 R squared, so we get A1 R squared times R, which is A1 R cubed. Similarly, A5 is going to be A4 times R, which is, of course, going to be A1 R cubed, which is what we found A4 to be, times R, which gives us A1 R to the 4. Now, if we generalize this, notice each term is going to be the first term, A1, times the common ratio to the power of a number which is 1 less than the term number. So for A5, we raise it to the power of 4, which is 1 less than 5. For A4, it's going to be A1 times R cubed, and 3 is 1 less than 4. Again, A3, you see, times R squared, which is 1 less than 3. All right, so we can generalize this. And of course, the most important element here is an, which is going to be A1 times R to the n minus 1. But I think it's good for you to always do one before and one after to understand this relationship. So what would be right before an? It would be an minus 1. And of course, it's going to be A1 times R to the power of 1 less than n minus 1. So that's basically n minus 1 minus 1, right? Like this. So where this n minus 2 comes from is n minus 1, which is, of course, n minus 2. So how about an plus 1? Well, this exponent here is going to be 1 less than the term number, which is n plus 1. So it's going to be n plus 1 minus 1, which is going to be n. So that's where those two terms come from. As we can see, the general term of the geometric sequence with a common ratio r is going to be an equals a1 r to the n minus 1. We can find any term of a geometric sequence if we know the first term and the common ratio. So this element here, this formula here, will be the second member of the toolbox we're going to need to handle problems related to geometric sequences. All right, here's an example to look at. Suppose a software company agrees to pay you $1 for the first day to do some coding for them, $2 for the second day, $4 for the third day, $8 on the fourth day, and so on, with your wages doubling each day as long as they are happy with your output. How much will you get paid on day 20 if all goes well? Well, if you think about it, this is the very same geometric sequence that we were talking about, the doubling one, right? So what do the terms of this sequence look like? Well, 1, 2, 4, 8, etc., right? So notice that A1 is 1, and the common ratio, of course, is 2, which we can obtain by dividing the second term by the first term or the fourth term by the third term. Makes no difference. Take any consecutive pair of terms and divide the one with the higher term number but by the one with the lower term number, and you end up with the common ratio. So we know that's going to be 2. So now we can we use basically this relationship to get our common ratio, right? If we want to show it, we did this basically. For example, we did 8 divided by 4 to get 2. And now we're going to use this to write the general term for this particular geometric sequence. And we know that an equals a1 r to the n minus 1. So in this particular problem, we know a1. a1 is 1 times r to the n minus 1. So if I want to know how much this individual will get paid, or you will get paid on day 20, I'm basically looking for A20, which is going to be 1 times r, we know, is 2 to the power of 20 minus 1. So we get A20 equals 2 to the 19. As you can see, geometric progression can be a very rapid type of progression, not necessarily similar to the linear kind of progression we saw with arithmetic sequences. So let's go ahead and see what that would amount to. So 2 to the power of 19. So that's how much you would get paid on day 20 if this pattern continued, right? So don't wait around for a company to be making that kind of an offer anytime soon. They don't come around too often. All right, so 524,288. All right, so if such an offer is made, obviously, definitely take it. All right, so that's a quick application of geometric sequences. All right, in this next problem, we want to find an and a7 for a geometric sequence with a1 equals 6 and the common ratio equals -3. All right, so we know that the relationship we need to use is this one, an equals a1 r to the n minus 1. Now, we know a1, that's 6, so let me go ahead and substitute that. and we know the common ratio is -3, right? And we also know A7, right, is the term that we want to find. So basically, I know that A7, if I replace n with 7, is going to be the first term, 6, times the common ratio to the power of 1 less than the term number, so 7 minus 1. So basically, A7 is going to be 6 times -3 to the power of 6, and we just need to compute that. So 6 times -3 to the power of 6. So we get 4,374. Now, as far as an itself, of course, it's very easy for this particular scenario, because we know it's just going to be a1, which is 6 times -3, quantity -3, to the power of n minus 1. So that would be the formula that would give us the general term an, and A7 in particular is right there, 4,374. Okay, so very simple, what fundamental, make sure you understand it, we'll proceed. All right, next we want to find the general term an and a5 for this geometric sequence, -5, -10, -20, -40, etc. All right, so the first thing we need to do is we need to find r, right? So we'll use this formula. So r, now I'm just going to take any pair, the first two are just fine. So well, I'll divide the second one, -10, by the first one, -5, and I end up with +2. So we know what r is now, and we do know the first term, that's -5, right? So we're ready to write the nth term. So an is going to be, we're using this formula now, so a1, which is -5, times 2 to the power of n minus 1. So there's the general term. Once I have that, I can find any term I want, right? So let's say we want a5, for example, in this case, right? So a5, just replace n with 5. It's going to be -5 times 2 to the power of 5 minus 1, right? So we end up with a5 being -5 times 2 to the 4. So that's -5 times 16. Don't forget the order of operations, always exponents before multiplication. So we end up with a5 equals -80. All right, and that's all there is to that one. All right, so here we have one with a little bit of a fraction action. Go ahead and see if you can figure this one out before you continue. All right, so we need an and a5 again. We don't have the common ratio. This is almost identical, right, to the previous one. I just wanted you to see that fractional situations are no different. All right, so here we'll find r first. Again, I can divide any pair of consecutive terms, but why not just go with the first two, because that'll be the simplest scenario. So I get a2, which is -2, divided by a1, which is 6. So we end up with -1/3 for the common ratio. And we do know the first term, that's 6. We're ready to write the general term, an. That's going to be 6 times quantity -1/3 to the power of n minus 1. So there's our general term, or an, and which is also the function that defines this particular sequence, right? And we now can easily find a5. we just replace n with 5 everywhere we see it in this formula. So we get 6 times quantity negative 1/3 to the power of 5 minus 1. That means 6 times negative 1/3 to the power of 4. Now that power of 4 is going to generate a positive result. So we get 6 times 1/3 to the 4 is 81, and it's going to be positive. And now I know that 3 goes into 6 twice and into 81 27 times. So we get A5 equals 2/27. And that's all we have to do there, okay? All right, for this next problem, we want the first term and the common ratio, which are not given. What's given is the 5th term and the 10th term, right? So let's see how we can go about doing that. Think about it for a few minutes. If you can figure it out on your own, then come back. All right, so we know that our general formula is an equals a1 r to the n minus 1. Let's start with that. Okay, so we do know a5, so let's go ahead and write up a formula using 5 for n. So we get a5 equals a1 r to the 5 minus 1, right? So that would be what? To the 4. All right, so I do know what a5 is. Let me substitute, which is 5. So I get 5 equals a1 r to the 4. Remember, we don't have either a1 or r, so we leave it as it is for now. Now we also know a10. So a10 is equal to 1 over, well, let's write the general form for it first. It's going to be a1 r to the 10 minus 1, which is 9, right? Now let me substitute 1 over 625 for a10, and I get 1 over 625 equals a1 r to the 9. All right, so we have these two scenarios. We have 1 over 625 is equal to a1 r to the 9, and 5 is equal to a1 r to the 4. There are different ways we can go about this point to try to solve this problem, but one of my favorite forms is just to go ahead and quickly divide these two equations. That will cancel out the a1s, and we should be able to get a value for r, right? So let's do that. So we get 1 over 625 over 5 over 1 is equal to a1 r to the 9 over a1 r to the 4. And of course we can do this because of one of the versions of the division property of equality, which says if a is equal to b and c is equal to d, then a over c is equal to b over d, as long as c and d are not what? 0. And we don't need to worry about that here because neither one of them are 0. So we go ahead and cancel out the a1s, and we end up with 1 over, now remember here, this is the scenario I showed you how to handle quickly before. It's going to be the outer product, which is 1 over the inner product. 5 times 600 is 3,000, and 5 times 25 is 125, so 3125. All right, And on this other side, we end up with r to the 9 over r to the 4 because the a1s cancel out. So you just get r to the 9 minus 4, which is r to the 5. So now all I need to do is go ahead and take the fifth root of both sides. So on the right side, we end up with r. On this side, in order to see what that fifth root is, we could utilize a calculator, but let's see if we can do it without. So we'll start with 3125 and try to find the prime factorization. All right, so I know that the sum is 4, 6, 11, so 3 doesn't go into it. So we'll start with 5 as a prime number that goes into that. 3125 divided by 5, we know that's going to be 625. And then divide by 5 again, you get 125. Again, 5 goes into it 25 times. Once again, 5 goes into it 5 times. And one last time to give us 1. So we can see that 3125 is 5 to the power of 1, 2, 3, 4, 5, right? So this is basically the fifth root of 1 over 5 to the 5, which is, of course, going to indicate that r is 1/5, okay? So now that we have r, we can easily get a1. We'll just use r and this equation. So we get 5 equals a1 times r to the 4. Solve it for a1. You get a1 is equal to 5 over r to the 4. So we get a1 equals 5 over r, which is 1/5 to the 4. So we get a1 equals 5 over 1 over, now that's going to be 5 to the 4, that's 625. So now again, we do the outer product, which is going to be 3125 over the inner product, which is 1. I don't need to write it. So there we have a1 and r. So a1 is 3125 and r is 1/5. All right, so a little bit more interesting than the simpler one that we have seen so far, but still quite manageable. So please make sure you can handle something like that on your own, and we'll proceed. All right, it was about this point in our study of arithmetic sequences that we paused and we asked a couple of questions. Why are arithmetic sequences named the way they are, and what does the word arithmetic have to do with those sequences? Now we're going to address the same questions for geometric sequences. In other words, why are geometric sequences named that way, and what does geometric have to do with these sequences? In order to understand the reason for the word geometric in the name of geometric sequences, we need to know the definition of the geometric mean of two real numbers. The geometric mean of two real numbers a and b is basically the square root of their product, okay? Now, a question may arise, a new one, namely, why is the geometric mean called that? Well, it has to do with geometry indeed. Suppose you have an A by B rectangle, like a plot of land or something of that sort, and you want to find a square of length m with the same area, so that you see the area inside here is the same as the area inside this A by B rectangle. So basically, we need to find this special number m, and of course we can do that very quickly algebraically, because we want the area of this square, which is basically m times m, or m squared, to be the same as the area of this rectangle, which is a times b. So then all we have to do is a quick application of the square root property, and we get m equals positive or negative square root of AB. But since we're interested in the positive area, we only take the positive case. So we get m equals square root of AB. And now we can answer the questions. Why are geometric sequences named that way, and what does geometric have to do with these sequences? A geometric sequence is named thus given that if you take any three consecutive terms, such as the ones that I show here, in a geometric sequence, the middle term will be the geometric mean of the other two. So in other words, here are three very general terms of a geometric sequence, and as you can see, the an minus 1 is the one that comes right before an. And for any term, you know that it's going to be the first term, a1, times the common ratio to the power of 1 less than the term number. So what's 1 less than n minus 1? N minus 2. And for the next term after an, we know it's going to be an plus 1, and that's going to be a1 r to the power of, what's 1 less than n plus 1? Just n, right? So here are three general terms of a geometric sequence. Now we're going to show that if you take the square root of the product of the term before an and the term after an, you actually end up with an, which is the geometric mean of an minus 1 and an plus 1. So note that if we take the square root of an minus 1 times an plus 1, that means the square root of what is an minus 1? It's a1 r to the n minus 2 times what is an plus 1? a1 r to the n. Now that's going to give us a1 times a1, which is a1 squared, times r to the, of course we're going to add the exponents because of the product rule, which says when you multiply two powers with the same base, keep the base, add the exponents, right? So we end up with a1 square root of a1 squared times r to the power of 2n, right? Combine the n's, minus 2. That means the square root of a1 squared times r to the, we're going to factor out a 2. That gives us 2 times n minus 1, which we can, of course, write in this way using the power rule. So we get the square root of a1 squared times r to the quantity r to the n minus 1 squared. And of course, since they're both squared, we're just going to get a1 times r to the n minus 1. But as you recall, that's just an. So there's a proof of why, given three consecutive terms of a geometric sequence, the middle one will always be the geometric mean of the two terms around it. Here's a quick example to demonstrate that. Look at, for example, this simple geometric sequence: 1, 3, 9, 27, etc., right? Notice that if I take, for example, the first three numbers, right? 1, 3, and 9, what is the square root of the first and the third term? Well, that's going to be the square root of 1 times 9, which is, of course, the square root of 9, which is 3. Notice the middle term. Or if we take these three numbers, as long as they're three consecutive terms, right? What is the square root of 3 times 27? Well, that's going to be the square root of 81, which is 9, again, the middle term. So this is why geometric sequences are called geometric sequences. All right, now we're ready to go ahead and talk about geometric series. And whenever you see the name series, you know summation is going to be involved. So that's where we're headed next. A geometric series is the sum of the terms of a geometric sequence. It may be necessary to find the sum of the terms of such sequences. For example, a scientist might want to know the total number of insects in n generations of the population of a certain species, which is growing according to a known geometric progression found by data analysis. So let's go ahead and see how we find these sums. Now, to find a formula for the sum Sn of the first n terms of a geometric sequence, we will use a trick that is similar to the way we converted repeating decimals to a fraction. Let Sn be the sum of the first n terms of a geometric sequence. That is, Sn is going to be a1 plus a2 plus a3 plus dot 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 plus what? An. Now, if I actually write out what they are, remember that's going to be a1 plus the second term will be a1r, the third term will be a1r squared, etc., all the way up to the an, which is a1r to the n minus 1. We now multiply Sn by the common ratio r to get r times Sn is equal to, just multiply every term by r. So we get what? We get a1r. Multiply this one by r, you get a1r squared. Multiply this one, you get a1r cubed, etc. All the way up to, we get a multiplication of the last term here by r, which is going to be like this. What is a1 r to the n minus 1 times r? Well, that's going to be a1 r to the, remember there's a hidden 1 there, so n minus 1 plus 1, which is a1 r to the n. That's why the last term here is a1 r to the n. Why is this one a1 r to the n minus 1? Remember, what's the term that comes right before a1 r to the n minus 1? It's a1 r to the n minus 2. What happens when you multiply that by r? You get a1 r to the n minus 2 plus 1 because of that 1 there. So we get a1 r to the n minus 1. So that's where this a1 r to the n minus 1 comes from. Now what we're going to do is we're going to subtract these two equations. So we get Sn minus r Sn is equal to, notice how all of these will cancel out, all the way up to what? To a1 r to the n minus 1. So you're left with a1 from the top, and then minus a1 r to the n from the bottom equation. And now if I factor out the Sn on the left side, I get Sn times 1 minus r equals a1 times 1 minus r to the n. So we get Sn equals a1 times 1 minus r to the n over 1 minus r, as long as r is not equal to 1. Now, this is basically the sum of the first n terms of a geometric sequence. Notice that if absolute value of r is less than 1, then what happens to r to the n? So if you take, for example, 1/2, right, to the n. As the values of n become larger and larger, right, what happens to the values of 1/2 to the n? It becomes smaller and smaller, right? And it eventually approaches 0. Hence, 1 minus r to the n, which approaches what? 1, because remember, this part is becoming 0. So, so 1 minus r to the n is going to approach 1 minus 0, which is just 1. So we end up with S infinity, which means the sum of all the infinite members of such a geometric sequence, the absolute value of whose common ratio is less than 1, to become just a1 over 1 minus r. So this works out really nicely as long as you have a common ratio whose absolute value is less than 1. Otherwise, we can find finite sums using this formula. So that is how we're going to be calculating these series. All right, so for our next example, remember the first example we did. Suppose the software company agrees to pay you $1 for the first day of work, $2 for the second, etc., right? Doubling each day. Now, we figured out how much you would get paid on day 20 if all goes well in example 1. Now let's find out how much you will have earned in total by the end of day 20. In other words, as you can see, we want to find S20. In other words, the sum of the first 20 terms of this sequence, 1, 2, 4, 8, etc., right? So as we can see, A1 is 1 and the common ratio is 2. So given that we have A1 and the common ratio, we should be able to figure it out, right? So we get S20 equals A1. We're using this formula, which is, let's just go ahead and plug it in, which is 1 times 1 minus 2 to the n, which is 20, over 1 minus 2. So now it's just a matter of computation. So basically 1 times anything is itself, so just 1 minus 2 to the power of 20, and we're going to divide that by -1, right? I did it in 2 steps, no big deal, it's the same thing. But we have to make sure we use this negative, right? The cursor is acting funny for some reason, but it doesn't matter as long as it gives us the right answer. So you would have been paid this much by the end of 20 days. 1,048,575. Okay, so that's how we find these geometric sums. All right, here's a more down-to-earth problem. Find the sum of the first 8 terms of the given geometric sequence. So of course it's going to be a finite sum. We're going to be using this formula, and we need to know what R is. We're going to use that formula to do that. So we know that R is going to be, we'll just take the first 2 terms, right? We'll just do A2 over A1, which is 15 over 5, so it's 3. Should be able to handle this. So it goes without saying, whether I remember to say it or not, at the beginning of every problem you should pause, try it on your own, and then watch what I do, because that's how you're going to get the most out of the class. All right, so we get that, and we do know A1, that's 5, and that's all we need for this formula, isn't it? Okay, so we get S8 is going to be A1, which is 5, times 1 minus R, which is 3 to the power of 5, 8 to the power of n, and then over 1 minus R, which is 3. Now it's just a matter of computation. So 5 times 1 minus 3 to the power of 8. We need to exit the parentheses and then put divided by 1 minus 3. So we get 16,400 for the sum of the first 8 terms of this geometric sequence. All right, that's how you do that. All right, here's another one. Go ahead and try this one and see what you get. It's no different. It just has some fractions. I wanted to make sure that you see one with fractions. We want the sum of the first 5 terms of this sequence, right? So we know that A1 is 6, right? And we can get R by doing A2 divided by A1. So we get negative 2 over 6, which is negative 1/3. So are we ready to find S5, the sum of the first 5 terms of this sequence? Yes, we are. So we get, now we're applying this formula, right? So we get A1, which is 6 times 1 minus negative 1/3. Make sure you use parentheses, to the power of 5, which is n, and then over 1 minus quantity negative 1/3, which is r. Okay, so it's not difficult. You just have to make sure you're careful when you type it into a calculator. All right, so we have 6 times 1 minus, I'm going to open another set of parentheses for the negative 1/3, and then we'll exit that first pair and then raise it to the power of 5. That's the nice thing about this calculator. You can just type it exactly as you see it, and then hit divided by, and then 1 minus negative 1/3. I'm just going to put 1 plus 1/3, and that's it. So there it is. Now that's a decimal number. I'm going to try to see if I can turn it into a nice fraction. So I'll hit that, and there it is. So 122 over 27. For the sum of the first 5 terms of this geometric sequence. Okay? All right, let's move on. All right, here we're asked to find this sum. Notice that it doesn't look like maybe it belongs to this section, but it actually does, because if you look at these terms, right, notice what we're actually adding. We're going to run through the values of j, right, starting with 1. The j values of interest are going to be 1, 2, 3, 4, and 5, right? We're going to run through these values and see what we get. So we get quantity negative 4 to the power of 1 plus quantity negative 4 to the power of 2, etc., all the way up to what? Quantity negative 4 to the power of 5. So notice, basically, this is a geometric sequence. The first one term is negative 4. The next one is negative 4 squared. The next one is negative 4 cubed, etc. And the fifth one is negative 4 to the 5. So what is the common ratio? Each term is being multiplied by negative 4 to get the next one, right? Or you can just think of it this way. Use the R formula. It's going to be just divide this term by this term. So we get what? Quantity negative 4 squared over negative 4, which is of course negative 4, right? So, and what is the A1 here? That's also negative 4. So we can find that sum of the first 5 terms of this sequence is basically what that is. So we're going to use the sum formula. Let's get A1, which is negative 4 times 1 minus the common ratio, which is also negative 4. Just happens to be that way, to the power of 5, which is n, and then all over 1 minus, again, negative 4, because that's the common ratio. So we just have to calculate that now. Okay, so we have negative 4 times quantity 1 minus quantity negative 4 and then exit that first parenthesis, raise it to the power of 5, and then exit all parentheses, and then hit divided by, that just becomes 1 plus 4, right? So we get negative 820. All right, and that's all there is to that problem. The main thing, of course, the realization of the fact that you do have a geometric sequence in disguise when you look at that sum. All right, in order to handle this next problem, I want to remind you about a property of summations that we learned, which was the sum from I equal 1 to n of c, some constant, times ai, is just going to be c times the sum from I equal 1 to n of ai. In other words, you can pull a constant out of a summation, handle the summation, and then multiply the constant by the result. That is going to make our work a little bit easier. It doesn't have to be done. It just makes the process and the numbers much simpler to deal with. So let's go ahead and do that first. So that means we're looking at 72 times the sum from I equal 1 to 4 of quantity 1/3 to the I. All right, so our focus is going to be on this sum here at first, because then we're just going to multiply whatever result we get by 72. So I notice that the terms of that are going to be added are going to be 1/3 to the 1, and then 1/3 squared, and then 1/3 cubed, etc., right? So it is in fact a geometric sequence. The first term is 1/3, as is the common ratio, because you basically multiply each term by 1/3 to get the next term, right? So this sum is nothing more than the sum of the first 4 terms of this geometric sequence. So now we're just going to multiply 72 by whatever we get for that sum, which we can get by applying this formula. So we get times A1, which is 1/3, times 1 minus R, which is also 1/3, to the power of 4, which is n, and all of that over 1 minus, once again, 1/3, because that's also the common ratio. So we end up with, let's just go ahead and type it in just like that. That's the nice thing, we can do that. All right, so 72 times 1/3 times, oh, we don't want to be there. We need to get out of the fraction there. So we're going to hit the right arrow once, and now we can put the parentheses again. So 1 minus yet another parenthesis for 1/3, and then get out of that parenthesis, raise it to the power of 4, and now we're going to exit all parentheses and then hit divided by 1 minus 1/3. Let's do a quick check, make sure we put it in correctly. 72 times 1/3 times 1 minus 1/3 to the 4, and then over that. That looks good, okay? So now let's see if we can turn that into a nice fraction. 320 over 9. All right, so there is that particular problem and how to go about it. Next, we want to look at a couple of infinite geometric series. Recall that if the absolute value of the common ratio r is less than 1, which means basically r is some number between -1 and 1, then the series will converge and it will have a well-defined sum. Namely, that infinite sum is going to be the first term divided by 1 minus the common ratio. We already derived that and showed where that comes from. Now, if the absolute value of r is greater than 1, the geometric series will be divergent and it will not have a well-defined sum. All right, so we're going to find the common ratio for this particular sequence and use it to determine whether the series will converge or not. And if it does converge, we'll find the sum. So r, of course, we can get using our very first formula. So for example, we can do a2 over a1, right? And we get 5 over 1. Now the absolute value of r here is 5, which is greater than 1. Therefore, the series diverges. We're not going to be able to get a sum out of that particular series. All right, well, it's going to be, basically, you can see this one, it's increasing without bounds, so it's going to be infinity, right? The sum. It's just not going to be a fixed, constant sum. All right, let's go ahead and move on. All right, we're going to repeat the process for this sequence. We're going to find the common ratio, use it to determine if the series is convergent. The sequence is convergent, and then if it is, we're going to find the sum. Now we'll use r formula here, so we get r equals, I can just do a2 over a1. So we get -9 over -27, which is 1/3. Now here, absolute value of 1/3 is just 1/3, which is less than 1. Therefore, this series converges, which means we should be able to use our S infinity formula to get the sum. So S infinity here, remember, we're adding infinitely many numbers, but the numbers are getting smaller and smaller. They're approaching 0. That's why we can actually get a sum for it, right? So we get equals A1. We're applying this formula. Okay, so A1 is -27 over 1 minus the common ratio, which is 1/3. And now we just have to calculate that. So we have -27 divided by 1 minus 1/3. All right, so let's go ahead and turn it into a fraction. So we get -81 over 2. There's the value of that infinite series. All right, let's go ahead. All right, try this one, see if you can get it, and then come back. All right, so we are gonna use our trick from before to go ahead and pull that 6 out. So we get 6 times the sum from I equal 1 to infinity of quantity 3/5 to the power of I minus 1. Okay, so let's see what terms are being added here. Okay, so we're going to run through the values of I starting with 1. So the first term would be 3/5 to the power of 1 minus 1, which is 0. The next term will be 3/5 quantity 3/5 to the power of 2 minus 1, which is 1. The next one will be quantity 3/5 to the power of 3 minus 1, which is 2. So you can see where this is going, right? It is a geometric sequence that whose members are being added. the first term is, be very careful here, it's quantity 3/5 to the 0, so it's 1. The common difference is indeed 3/5, because then you start multiplying every term by 3/5 to get the next term, right? Now, the absolute value of 3/5 is 3/5, which is less than 1, therefore the series is convergent. So we should be able to find the sum using this formula. So basically, this is going to be 6 times s infinity for this sequence, right? So we get basically the sum of all the terms of this sequence, which becomes a series, right? So it's going to be 6 times, remember, a1 is 1, not 3/5. Be real careful with that. Over 1 minus, now r is 3/5, so now we're just going to type it in. Of course, it's great practice to do all these things manually to keep your arithmetic skills fresh, but the videos would never end as is if we wanted to take the time to do that every time. So 6 times 1, which is just 6, divided by 1 minus 3/5. So we get 15 for that particular problem. Don't forget the 6. It's very important not to get, caught up with the sum and the fact that it's equal to s infinity and then forget the 6. So make sure you don't forget the 6. All right, that's how you do that one. All right, here's a fun problem to end our day with, our lecture with. Each person has 2 parents, 4 grandparents, 8 great-grandparents, and so on. What is the total number of ancestors a person has going back 5 generations? And then we'll figure it out for 20 generations. So you should definitely be able to do this. So go ahead and see if you can do it on your own, and then come back and compare your answer with mine, okay? This is, I'll give you a hint. It's really simple, okay? Okay, so let's take a look. Do we have a geometric sequence here? Well, let's see. What do the terms of this ancestral sequence look like? Well, we start with 2, right? And then 4, and then 8, 16, etc., right? So we do have a geometric sequence. The first term is 2a1, as is the common ratio, because just divide a2 by a1, right? So basically, to answer the first part, we're looking at S5. We're going to be using this formula. So we're going to get A1, which is 2, times 1 minus 2, which is the common ratio as well, to the power of n, which is 5 in this case, over 1 minus 2. Let's go ahead and calculate that. So we have 2 times 1 minus 2 to the power of 5 exit divided by 1 minus 2. So you have 62 ancestors going back 5 generations. Now it gets more interesting from there. So what would S20 be? Let's go back 20 generations. Let's see how many people have been involved in your existence on this planet just going back 20 generations. So we get 2 times 1 minus 2 to the n, which in this case is 20, and then over 1 minus 2. So we'll use a nice feature of this calculator to just copy that. Just double click it and it copies. And we're just going to change this 5 up here to 20. All right, so going back 20 generations, you have 2,097,150 ancestors. All right, so quite an interesting one to wrap up our day. All right, so I hope you learned much, and I'll see you at the next lecture.